All right, it's a really great pleasure to be here today. I'm going to try and give you a brief snapshot of some recent work where we're trying to really understand what happens, what are the primary atomic scale and real-time events that happen following absorption of a photon in these very exciting materials for next-generation photovoltaic devices and so on. As I'll try to show you, these kind of measurements, which allow us to visualize what's actually happening, can actually have a direct impact on our understanding of the functionality of these materials, the unique optoelectronic properties and efficiencies and degradation mechanisms, and so on. If you ask someone, what does the structure of one of these materials look like, they'll maybe show you a picture like the top left there. You have these kind of corner-touching octahedra. This is the prototypical structural methylammonium lead iodide. You have these corner-touching octahedra. Sitting at the interstices, you have these organic cations. So that's the sort of crystal structure as you might define it. But now on the middle plot there is an actual MD simulation, and you can see that the structure is just as much a liquid as it is a solid in some sense, right? And so there's been a lot of discussion in the literature about what are the role of these kind of dynamical fluctuations? How does this impact the optoelectronic properties of these materials? What I'm going to show you is actually an additional surprise, and that is that when a photon is absorbed, when you shine light on one of these materials, you trigger a very interesting and dynamic large amplitude structural reorganization, a kind of rotational disordering that we call it, essentially a large amplitude distortion of these inorganic octahedra. And I'll try to show how these measurements can, in part, help us to start to understand the unique optoelectronic properties, the efficiencies of these materials. So how do we do these experiments? Well, this is an experiment done just up the road at the SLAC National Accelerator Laboratory. We use a femtosecond optical pulse. This is kind of a prototypical pump probe experiment. A femtosecond optical pulse excites a thin film of these materials, and then we probe the structure with a femtosecond bunch of electrons. So we're doing electron diffraction, and of course from the measurement of the Bragg peaks and so on, we can work backwards in principle and actually reconstruct where the atoms are and what they're doing in real time. Here's the kind of rough measurement. So there's a lot of data here, and I only have a short amount of time to describe it. But the black curve up there is the, I have a laser pointer here, I guess. The black curve, well, maybe not. Here we go. The black curve is the static structure of these materials. The red curve, maybe zoom in on that. This is the differential change measured about 70 picoseconds after photoexcitation. You can see there's a complex kind of range. Some peaks are going down. Other regions of the scattering pattern are going up. From this measurement, we can essentially, by doing an inverse Fourier transform, we can extract what's called the pair correlation function. This encodes the sort of short-range atomic scale correlations and how these are changing as a function of time. So to understand what's happening, I'm first going to show you what the static pair distribution function looks like. That's over here. Essentially, you have a peak, for example, right around 3 angstroms. This corresponds to the distance from the central lead atom to one of the neighboring iodine atoms within this inorganic octahedra. You have another peak at around 4.5 angstroms. This corresponds to the body diagonal, one of the diagonals, the distance separating one iodine atom to the next. So this is a static structure, and of course you have higher order correlations as well. So what's happening as a function of time? Well, here's the kind of main result of this measurement. And what you see is actually a really dramatic structural change, quite surprising. We weren't expecting this at all. So there's a very large amplitude dip right at the iodine-iodine bond length, 4.5 angstroms. So this says that we're dramatically kind of washing out those correlations following this optical excitation. In contrast, there's very little change at the lead iodide distance. So what this says in kind of a very kind of coarse way is that absorption of a photon drives very large amplitude rotational disordering, a kind of a distortion in which the iodine atoms kind of move on the surface of the sphere. This effect kind of completely dominates over any kind of thermal effect in the material. This kind of light-induced volume-preserving distortions actually really dominate the kind of photon-induced structural response in the material. So let me spend a couple of minutes and just talk about the summary of what we've learned from these measurements. So the first thing is that from these measurements, we're essentially directly watching the transfer of energy from electronic excitations into the lattice. And so from these measurements, we can directly extract things like hot carrier lattice coupling. This is important with respect to understanding hot carrier solar cells, the processes which determine the Shockley-Queisser limit, these kind of entropic thermalization processes that in the end determine these kinds of efficiencies. These timescales occur on roughly 10 to 20 picoseconds. And then kind of most surprising is this kind of observation of this dynamic rotational disordering. The kind of key takeaway here is that it's not enough just to consider these kind of intrinsic dynamical fluctuations that occur in these materials, and that actually absorption of a photon drives really large amplitude structural reorganizations. These occur on picosecond timescales. We think these processes are happening really every time a photon is actually absorbed in a photovoltaic device. There are a number of ongoing experiments. We're probing a number of other related materials. There are actually a lot of interesting complementary techniques, all from the perspective of kind of all optical probing of these processes. These materials, for example, are interesting terahertz emitters. So every time a photon is absorbed, they emit with quite high efficiency terahertz photons. And these photons, in turn, actually also encode these kind of structural distortions. This is one of the ongoing works that we're working on right now. And then in terms of the future, it hasn't escaped our attention that, of course, the iodine atoms in these prototypical perovskites are oftentimes the key mobile species that actually in the end determine the eventual degradation mechanisms and the lifetimes of these materials. So we think that in some sense we're kind of capturing the first steps in these ionic hopping events that occurring on kind of picosecond timescales. And then really from a very general perspective, we think these measurements can provide a new kind of feedback between between synthesis and sort of the design and engineering of new materials and kind of real-time feedback of the kind of fundamental processes that in the end determine the ultimate efficiencies of devices based on these materials. So thank you very much, and I'll hang around afterwards. Happy to take any questions.